Okay, here we go with Programmable Controllers 3, Week 2. And we're going to call this Machine Control Review. We're going to be going over some safety stuff and just getting back into the Logix controller. So attendance, I can take a look at D2L to see where you're at, and I'll have you sign in. They're going to be new handouts. We're kind of going as we go here. I'll get you homework and labs and stuff like that. I'm trying to populate D2L as we go. Just let me know if you have any questions. The safety policy, I'm going to have you guys sign this and turn that in. We'll review it quickly. The main thing to think about is that I know that this is mostly 24 VDC, which is a lot safer than using 120 VAC, but I still would like safety glasses on. And in this next lab, for example, we got a little bit of three-phase going, and I think the safety relays are 120 VAC. So we just want to be careful. Be sure to bring some safety glasses to class when you're working on this, and keep things energized and de-energized as they're supposed to be. What we're going to do is we're going to do a week 1 review. And we were talking about we started with kind of the Ethernet setup and network design, talked to getting things hooked up through a switch. And so I just want to show you, once again, what we're coming through. This would be called a star network because we're using this Stratix 5700. Now, the routing is not enabled. So everything that we put in through this switch needs to have the same network, which is a 192.168.1 network is what we're using. Could be, we could use a different network. We could use a 172.16.1 network, as long as the last numbers are all different. Okay. Now this one right here is showing different VLANs, because you can see that this is a .10 network, and this is a .11 network, and this is a .1 network. So we're going to get to this in probably week 4-ish, where we get this going and we have different networks. But right now we don't have that going. And then we talked about briefly about the network gateway. So this is going to be, our switch, and then this is going to be our computer. So when we when we get down the road a little bit, we're going to set our network gateway to the IP address of the switch, okay? Because the switch is what we use to reach out to the different networks here, okay? So if your switch already has an IP address on it, you can leave the network gateway blank, or you could put the network gateway of the switch in, and it will work, like an unmanaged switch that it is right now. Later on, we'll get into this network gateway, but hopefully you understand what the network gateway is. The network gateway is how are you reaching out to the network. So if you're just reaching out to the World Wide Web, your computer here or the LCC LAN is going to have a network gateway of how it's reaching out to that. We'll get into it a little bit more. But we did, do how you do static IPs. How do you access the network and sharing center? And so we were having some problems here being able to type in things here, depending on if you could get logged in or not. But maybe we were getting it from the control panel coming here, and I see. A lot of times it's going to default to small icons or category or large icons, whatever. But this is the kind of the nice look here. If you go to category, that's not as useful, I don't think. But if we go to large icons or small icons, you can go to network and sharing center. And once again, here's change your adapter settings. And then you can go and change, what you got going. I'll just plug in a USB to Ethernet adapter here real quick. I just plugged one in, and there it is right here. That's my USB. And that's where I was talking about, that you could come in here, go to properties, go to your TCP/IP4, give it a static IP address. It'll automatically populate your subnet 255.255.255.0. But if you wanted to put in a default gateway coming through your managed switch, you could, but we don't need to do that right now. But we will be getting to that. So that's how do you get into your network and sharing center to change those adapter settings? And then we talked about, once again, all our equipment's on a static IP address. We're using 192.168.1 something, versus we'll keep the computer at DHCP. It's just dynamic, and it's reaching out to the World Wide Web. So along those lines, we took a look at some new equipment, and when you get a piece of new equipment, from Allen Bradley or whoever, it's got DHCP enabled, okay? And what that's doing is just dynamic. It hasn't been assigned a static address yet, and so we like to go ahead and assign it. So one of the things that we could do is use boot P, and we had a little bit of success here, not success. If your unit already had a static IP address on it, 192.168.1.11, for example, well, that means that the DHCP is disabled, so boot P won't work. You need to have something where DHCP is enabled. Okay, so if you're using boot P, you know, we talked about you want to clear the network out, just plug directly in the network. And one of the mistakes we were made is on boot P right here, you need to set your computer to a static 192.168.1- let's say 20. And that way, when you assign an address 192.168.1, let's pick a different number, 10, then it's in the same subnet and it will work. But if you had a dynamic, then it was trying to push the subnet into the dynamic subnet of your computer. So make your computer static, okay? Now, and it's a big pain in the butt. I gotta tell you, boot P is a pain in the butt, but sometimes that's the only way you gotta do it. And you gotta run it a few times, get it to go. You gotta cycle power on it, because that's really what it takes when you cycle the power. You disable a DHCP, cycle the power on the boot P, and then hopefully it comes up and gets it. If it doesn't, you do it again, Man, I've had to do it like 5 times or more, you know, then all of a sudden, boom, all of a sudden it's got the Ethernet address. And then from there, once you got Ethernet, you can go to town on it and you know, make, you can even change the IP address from there if you want. If you know what it is, you can do revisions, all kinds of stuff, right? Pain in the butt, but it does work. And then the easy way is USB A to B. Everything's just plug and play. So we just plug some stuff in. So that's the beauty of the new stuff. You can plug it in. You can get into links. You can change. You can set a static IP address. Boom, boom, boom. Yep. But remember, if you don't have that, you want to set your NIC to static when using boot P. Just be sure to change your computer back to dynamic when you get done. All right. My computer, my laptop here, man, I change the IP addresses static dynamic a lot on it, and sometimes I'm like, God, this thing's not working. What happened? Oh, I forgot to change it back to dynamic so I can connect to the World Wide Web. We did some firmware revision here. Once again, equipment comes shipped with basically no firmware revision on it because, hey, you might be using, you know, maybe you've only purchased, you know, Logix 24, 26, or 28, or 32, or whatever, and that's what you want everything running on. Or maybe you're cloning equipment and you want that revision. So you got to flash it. It's coming on firmware 1. You got to flash it to what you want, and you can update the firmware using Control Flash, which is the old school way of doing it. Now, the thing about Control Flash, in my opinion, it's really pretty bulletproof. It does work well. Control Flash, if you got your network set up and it sees your network, and your network is going to be Ethernet typically with Control Flash because it's older, it's great. But the problem is you have to go to the RA Download Center and you have to get all those drivers that you want, and then you got to put them into the Rockwell Automation firmware folder. And then that way, boom, when you go to Control Flash, it's going to be there. Now, the newer and nicer one is Control Flash Plus. Now, I don't know if it's quite as bulletproof as Control Flash. For some reason, I know I can get Control Flash to always work if I download the correct firmware. Control Flash Plus, I'm about 99% on. And if you log into RA Download Center and you use Control Flash Plus, you pick your path, it does pretty good. It's just, I don't know what it is. I mean, Control Flash Plus has got so much other functionality of building libraries, and you can flash like 20 things at a time with Control Flash Plus. But here, Control Flash, you're only doing one at a time. This, you can just have multiple things going. So it is cool. It does work better. And then when we're doing this, we can connect using Ethernet or USB to B. And so the problem, once again, with the Ethernet, if it doesn't have the USB to B, you got to get it all set first. If you happen to have USB to B, bang, you're in business. You can do either or. Okay, you can do the firmware revisions and the IP address. All right. So I put the Control Flash plus manual on D2. I'll ask you to read it and glance through, maybe half of it. You can see it's very extensive. As a matter of fact, I don't know, maybe at your company you'll be in charge of this kind of stuff, and maybe you'll be the expert on it, but it doesn't hurt to know it. But there's a lot there about creating a library for use offline, or else if you connect to the download center and you get gray, red, or green indicators or blue indicators to indicate, how you're connected and all this kind of stuff. The manual went through and described all that. A couple things. So Studio version 37 is the latest, that they've released, and I've loaded this up onto your computers, and it brings in all the latest firmware definitions. For example, Mark, one of the students didn't have 37 on his computer. I think he only had up to 28. So when he put in the bridge, the latest and greatest EN2TR bridge, well, guess what? This bridge didn't exist. This was not a product that Allen Bradley had available at the time version 28 was released. And therefore, when you tried to see what this was, connect to it and find out what's going on, you got like a yellow question mark on links. Like it didn't know what it was. It could kind of find it and work with it, but there was a lot of problems with it, and you would have had to set it up manually. But when I downloaded and installed version 37, it updated all the firmware data. And so after that, when you go and you connect to EN2TR, and when you go to links, it shows this like it should. It populates and everything works just great the way it should without having to load up any other files. Okay. So that's the beauty of having the latest on there. You get all the other firmware. But if it's not available, you can download and save it into the Rockwell Automation directory. And so for this example, if you have 28, but you have an EN2TR and it's not available, go out and get it, download it, update the firmware, get it all set up, and it's likely you might have to update some other software on this, and we'll go over how to update it so Links really is happy with everything that it's looking, but that takes care of the problem. We talked about the Common Industrial Protocol, CIP, and so you think about the CIP being on the application layer. It's actually involved in a couple of layers, but the application layer is the big one. Of the OSI manages the interaction between programs and applications on the network. So we have different programs that we've been using on the network. A couple that we talked about are just our internet. We haven't done any control net, but we have done device net. So this CIP, it's an Allen Bradley concept that came up with this, and it talks about how all this managed. And basically it organizes and represent the data, managing connections, facilitating messages on the network. And once again, I talked about, device net was a good one that we did, last time. But there are 4 industrial networks, sometimes referred to as SIP networks. And the one is the Ethernet IP, and it just implements SIP over standard Ethernet. We're going to be doing a lot of that in this class, just Ethernet IP. SIP can be applied over a CAN network. And so a CAN network, for example, was device network, and it was just your local. It was just a local network. We weren't reaching out to the World Wide Web or anything like that. It was just a CAN network, and CIP has all the protocols and everything to get this to work. We talked a little bit in class about ControlNet. Uses a concurrent time division multiple access. So ControlNet is a redundant network. So when you hook things up, there's 2 channels connecting it, so it's a little more stable. There's the way it manages data. There's not as many errors. It just, if you really want your data between your field devices or your controllers moving back and forth between your network devices, ControlNet's just a little more secure, a little more stable. And then we talked about here time-driven items where the network, there's certain broadcast times where you broadcast and another one broadcasts and another one broadcasts. So it's not a collision network or a token sharing network. We talked about you know, this being a collision and device event being token sharing. This is all timed. So those are some of the types of networks, and hopefully, you know, everything that I just said kind of made sense to you. And if not, you can take a look in your textbook about the different types of networks, or take a look at your ELTE261 about, you know, what is a token network or a collision detect network. You know, what is Modbus, you know, stuff like that. Okay. So it says review homework. The homework's pretty good. I just threw some basic questions out there to get you to dig into the Control Flash Plus manual. So the Control Flash Plus manual is pretty large. I maybe asked you to read half of it and kind of look through and see what it goes. Like I said, you could go to town on this baby and just be an expert on Control Flash Plus. I'm not. I just use it every once in a while when I want to update some firmware. I don't need to have huge libraries that I'm, you know, flashing entire facilities, but it certainly happens a lot, you know. And then I had you read the Allen Bradley Network Basics, because we're starting to do more and more networking to talk about, you know, how the CIP, the Common Industrial Protocol, works, you know, with these different networks. All right, capstone review. So I wanted to take a look at, you know, the prior capstone that we did. If you remember, we had a variable frequency drive, we had an HMI, a different controller, and what I wanted to talk about was, you know, subroutine, schedule, and local and controller tags, local and remote I/O. So as we get going here, you know, this is a 24. So once again, we're going to have a main task, a main program, and we're going to have just a lot of subroutines here, organizing the stuff how we want it to go, probably unconditionally called out of the main routine. And then when you generate this, we're going to have, you know, our module defined I/O. We're going to be using a lot of rack-based I/O, okay? But we're also going to be using some remote I/O, because when we get to safety I/O, it's a lot easier to incorporate Ethernet IP, remote Ethernet IP safety I/O, instead of having, well, you can do it. You can buy the cards for local rack. They're just expensive, and you know, then we had to make up a bunch of connections. So we've kind of got those remote Ethernet IP set up. So once again, we have our module defined, and this is going to be I/O. When you bring I/O, it's module defined, and it's going to be globally scoped tags. Now, whether you come into each of these inputs and when you map them, whether you make those globally or global controller tags, you know, you can name this as motor starter 1, motor starter 2, motor starter 3, whatever, versus the alias versus the base tag. Remember what the base tag is. The base tag is the actual data point that's going to be module defined, globally scoped tag. Or if you make your local tags, whether you want to do local tags or whether you want to do global tags, that's something that you're going to start getting into and figuring out where you're at. And so once again, this is what our I/O configuration is going to look like. We're going to have some local stuff, and then we're going to have some remote Ethernet IP. Now, this is just, it's nice. It gives us all this information about the tags, tells us whether they're globally they're controller tags or whether they're the local tags for the program. But you know, it generates a lot of crap when you do here, and a lot of these are self-generated. You didn't have to create all these tags, but when you go for troubleshooting, you do need to figure out, you know, what everything looks like and where to find it. So this looks like a main, right? You're just going to have some JSR where you map your inputs, your general, your functions, your automatic parameters, everything like this, and that's kind of what the mains are going to look like. And the only other thing you might put into the main is you might put in a timing circuit. Sometimes people put in a timing circuit that if the program is in run mode, that it keeps track of how long it's been running. Okay, so sometimes you might find like you might find some basic safety like lights or something in the main here, but you know, like I said, you might have a timer in there to keep track of how long it's running, but a few other things. In maybe your general routine here, what this is doing is it's setting your state manager, and we're going to get in state manager in like weeks 5 and 6, okay, and we'll talk about this is SFS. This is a status bit on the first scan. So every time you go into run mode, whether you download it and hit run, or whether you do it with the key off and on run, on the very first scan, it only does this once, and it might, you know, do some type of resetting or getting you ready to run and stuff like that. Okay, so that's some basic stuff that's going to be in your general related to how things are going. Now on this general one, I see that people like to program. You like to put your system bit or your system running into here. So you take that system bit, and often tied, maybe often tied to your safety relay status or your safety systems, that safety bit, and then you incorporate that into the rest of your subs. So maybe that goes into this general here, just your system. Could be a way to without having to repeat all that logic over and over and over into your different subroutines, you know, some type of your system. Okay. This one was a little more extensive. Let's see what else we got going here. If there's anything else I wanted to show you, maybe I'm into different subroutines. Remember, this was where we were sorting blocks with holes without trying to get a certain status. Now, as we go with our state manager later on, this is going to even look a little bit different. So here's my automatic routine, for example. Notice that, yeah, you're probably doing a good job here with your labeling. Notice your run comments. Because even as I scroll through this capstone project and you did it, it looks pretty complicated here. Like, you're like, man, how could I even figure out if this thing is working or not? Well, the key is to really go through and label stuff as much as you can. All right, let me go down to the bottom of this and see if there's anything else I need to know. General outputs. Oh, we'll talk about mapping your inputs and outputs here in just a second. But yeah, that's kind of a little bit of an example of some of the programming. Notice once again, this keeps going. This is a lot. There's a lot of programming in this item right here. You might want to copy this routine. This is your date and time parameters. Once again, this is built into the processor. So if you want to put the time, you can get your wall clock time. If your CPU is set to be synced up with your computer or with the World Wide Web, it'll pull in the date and time. So this is a nice feature right here to have the date and time. You might want to throw it up on the HMI, or you might just want to use that to log, you know, when your processor was running and when it wasn't running. Here's the synchronous file copy, and we're going to be going over this for I/O mapping today. We'll dig way into it. Here's my mapping of my outputs routine, and we're going to go talk about, once again, synchronous copy of, you know, you're taking your outputs and you're putting your destination into your data. So we'll talk about whether you want to map the inputs or outputs, and then, you know, so that's once again a good example. It's here. This is on the D2L. So if you want to review this as you move forward, and you want to figure out, maybe I should do this or that, how they do it here, how they map their outputs, how they map their inputs, how they do the date and time, you can take a look at it, and there's some stuff here. So that's a good little resource for you there. Okay. So once again, scheduling. Yep. So I showed you there, we're going to be scheduling stuff. We'll be putting them in subroutines, and/or we'll be doing more add-on instructions as we get going. We'll review the add-on instructions. We'll probably do the analog lab again, because we're going to be doing a lot of analog, and we want to be sure we understand analog, and that has the add-on instructions. We're also going to use the phase manager in later labs. The phase manager is another way, another scheduling mechanism. All right. So I/O mapping. In this lab, we're going to be talking about I/O mapping. And remember, it's required because there's two different asynchronous scans for the logic and the I/O. Logic's an asynchronous scan. I/O is a scan. There's two other scans. There's 4 scans going total on this, on the control logics processor. We'll get into those later. But once again, we're talking about the I/O, the actual reading of the signal from the field device, the electrical side of it, and then the logic scan, which is all fictional. And so when we looked at this, we had PB5, PB5, you know, this was open, this was closed. Was it possible to have these both on at the same time? It is, because electrically they could be read into the scan at a different time than when the logic was solved here. And so you could get light 1 and light 2 on. Now that could be a problem. You know, light 1 and light 2, that's not a big deal, because by the time light 1 came on, and this scanned so fast, be sure to understand, by the time light 1 came on and it went through and scanned and updated this and put light 2 on, or vice versa, you would never see the light come on. And you would never see this light. The light that was supposed to be on would be on. The other one, you wouldn't actually see it. But it would have came on for a scan, or until those scans sync. Now, a field device, it doesn't matter. But if these were like bits, and these bits were used for logic, or these bits were used for latching or unlatching, or bits used for memory, or to break memory, something like that, then you got a problem, because there's a possibility that that bit could have been both that same bit could have been on, or those different bits could have been on, latching something on and unlatching something else that you didn't think it was. So the input is critical. And there are different ways to map the I/O. The most basic involves mapping an input base tag to an output bit, and that's what we did here. We took the actual base data, input to local 2 data 0, and we mapped it to a bit. And so when that bit comes on, it turns on the actual, light 1, it turns on the logic, and once again, that's fictional, but it is connected to an electrical device, light 1, okay? And so what this did is we basically took all the inputs, and when that input scan goes through and it reads the signals, this whole routine is going to be executed at the same time, and all the actual condition of the electrical device, whether it's got current through it or not, and is reading here, gets put into the logic scan, because this is fictional. And so once you're in logic scan, it's all logic. It's all executed at the same time. Okay, so we basically force the electrical signals. I guess if you want to do it that scan, you kind of force it into the ladder scan, and that's the way we map the I/O. Now, in this lab, what we're going to do is we're going to do a synchronous copy. Okay, and what you're going to do is you're going to take your local input, your local data, and because it's got date, it's data. It doesn't say data.0, data.1, data.2, data.3, whatever. And we're going to put it into the inputs. Okay, and the lab shows you how to go in there and add information about this is push button 1, push button 2, whatever. So, and I just want to make a point. When you do this, can you try and be clear as to what your tag name is? That really helps. Like if you say S1, S2, S3, S4, is that sensor 1, sensor 2, sensor 3, sensor 4, safety 1, safety 2, safety? Just if you put a little bit of a description in there, it's going to help you and it's going to help me. Okay, so synchronous copy is a way that you might want to do that. Now, in the last class, some people were using the move command, and basically they kind of had the idea that they were just going to move the local data into a destination, a word called inputs. It's almost just like this, right? The big difference is the execution integrity of using a move versus a synchronous copy. And I'm going to pull this up, and this is going to be here. You can come and check this video at any time and slow down or watch it again and pause it. But the difference between the move and the synchronous copy is data size, data handling, execution integrity, right? It's designed to move safely, transferring large chunks of data without interruption, where a move is really good for simpler single element data transfers, okay? And so synchronous copy, there's no conversion, internal bit for bit copy, whereas this automatic conversion interprets the source and represents it, okay? And it talks about the data size here between the two. The move-like behavior, you would need to use a loop or differentiation FAL. Just to get into it right here, you want, it depends on how you're going to move your data sizes. But the big one here is the execution integrity. Atomic operation. This is the synchronous part. The PLC locks the destination tag during the copy, preventing other program tasks from reading or writing it until the entire copy is complete. And so because we have an asynchronous scan, you don't want something happening during the move and you're like, crap, how long can that move command take? Well, if not very long, but if the scans aren't matching up and it executes the ladder scan in the middle of the move, the IO electrically is being updated, then you got a problem, right? And so it can be interrupted. The operation can be interrupted by other process texts, higher priority routines. This locks it. And then when you use instructions, use synchronous copy when you need to move large arrays. You're transferring data types read by another task. And in the move, once again, is great. We're going to use some moves. If you're transferring a single element, integer, float, boolean, will you be using a lot of moves? It's great. It will convert the data. That's another thing that's really interesting. Remember that, like if you moved a dent into an int, some of these things, remember it truncates. It's going to truncate your data to match the destination. And so just be aware of that when you're doing some of this moves. The data types gotta match, right? So that was a little. We'll be using synchronous copy for this, and a little bit different than a move. Okay. Mapping of outputs. So, do you need to map your outputs? So, we're gonna chat with this just a little bit, and I'm probably taking longer than than it should. But if I'm having an input turn on an output. So this is I1. Let's say it's mapped. Turn it on output 1 not mapped. Okay. Well, you got two things. Number one is this is hooked to something on the output module. Let's say it's hooked to a control relay. Okay. So this instruction is going to come true, and that instruction is going to come true immediately when that scan is executed, when the IO scan is executed. Okay. And then a short time later, or depending on how they're synced up, the output module is going to get written with a 1 right here, and the light's going to come on, and the control relay is going to come on. Now, when that control relay comes on, another thing to keep in mind, there's a measurable amount of time that it takes for this relay to close. You could get a stopwatch on it and try and time it. It's not going to be very long, but it does take some actual time for this to move through space and to close. So you think, well, it did take some time for this to get written true in the IL scan, but it's darn fast. It is going to be darn fast that this gets written compared to when it gets scanned and updated electrically when the control relay comes out. So we got a little bit of a time issue involved. So if you take this output 1 right here and you want to have this turn something on, well, that's a little bit of an issue. If for some reason you have this control relay wired into the input module as a contact, let's say you were monitoring it, and let's say this output 0 was really input 1 right here, okay, well then there's certainly going to be a delay. By the time this comes on, gets written, this turns on, this closes, and then this becomes true, there's going to be a delay of, I don't know, hundredth of a second or something. It's going to take some time where there could be some scanning going on to turn on the next thing here. But assuming that that's not the case, what about this being part of the ladder scan, that this is going to come on, and then it's going to start the next scan. It's going to see what's on, and then it's going to write this as being true, and then it's going to come and turn on the next thing right here, light 1. Okay. And so all these factors are something you got to think about, because we talked about having just a minute ago of having this 2 different lights on at the same time, even though you'll never see the other light come on due to the way it was mapped. But if you did this and you had O1 open, O1 closed, light 1, light 2, Well, you're kind of in this, you're kind of thinking the same thing, like, okay, who cares? You know, this light is going to come on, but by the time this gets written, this light is going to be off, or does that apply to this skin or not? You'll never see the two lights on at the same time. The light that's supposed to be on is going to be on, the one that's supposed to be off is going to be off. But if this is bit 1 and this is bit 2, well, maybe then it's important because, you know, if bit 1 down here is being used for some memory, let's say bit 3, well, then it's going to come on. But if bit 2 is supposed to break this, and then it's supposed to do its own memory down here with, you know, I don't know how this is going to work. You know, bit 4 coming on bit 4, and the bit 1 is supposed to break this. I mean, you could get into some weird things going on here depending on how this scan is all hitting and what's being timed out and whatever. So if for some reason you do move this into a mapped output, there's a couple reasons to do it. Then you definitely know that is going to be all executed as you think it's going to be, you know, executed. And a lot of times I don't do the outputs anyways because they're kind of executed at the end. They're part of the ladder logic. They're kind of updated anyways. All right. But if you think you're going to have an issue depending on how you're using that information in your program, you can map them to the outputs. Another thing is just the organization. You'll end up with a similar organization that you did for your mapped inputs. It's going to have the same structure, the same feel, and so when you look at your program, it'll look the same. So we just talk about, you know, maybe there's some scan considerations to think about. And so when you talk about, you know, scan considerations and issues, you just want to give you another prime example of how you can get in trouble here with the PLC, and that's the break before you make, or do you make before you break? And so this was the car wash. You know, you'd be doing the car wash here, and this is showing, you know, physical manual devices that with contacts are closing, contacts are opening, items are coming on. So, you know, just to reiterate, this car jog, this is from 131, this button right here kind of, I guess, enables or disables the memory branch. You know, we did it with a selector switch to kind of switch between those. But basically, if you're not pushing it, well, then the memory rung has a possibility of becoming true. So when you hit start, boom, it runs. Okay, and then you can hit stop and turn it off. Versus the jog, you know, you can just bypass, you go on the other rung and you bypass this contact, even though this is coming true, even though the contact's closing. You know, when you push this down to here, it's running. So what happens on the PLC if you just program it like this? Well, remember, it starts by looking at the inputs to see what is going to be true on the ladder logic, and then it updates the outputs. Okay, and so for this is a relay contact as shown here. This is hardwired. So in order for this to close, this has to first of all come on, and in for this to turn off, well then first of all you actually have to turn off the M1. And the PLC is looking at it the same way. And if you convert this to PLC, in order for this contact to close, you must first turn on the bit. And in order for this to open, you must first turn off the bit. So if you did this with a PLC, what you're going to get into is a race. What happens first? When I let go of the car jog button and it snaps back closed here, when I push it, you know, I'm pushing it slowly, so that's going to take some time to close. But when I let go of it and it snaps back, what's faster? The time it takes to snap back or the PLC scan? Well, the PLC scan is probably faster than the the amount of time it takes the spring to close that push button again. So if you do this in ladder logic and you push start, you get a path here, and the bit comes on, the motor M1 bit, and then it writes the logic, and the M1 bit comes on here, and this is true, even though we're using the bottom here. So when I let go of this and it snaps back, well, remember, first of all, this has to turn off at the end of the scan, so that at the beginning of the scan, this has to then be seen as off. But if you bring this back right here, as soon as you break it, as soon as it breaks here, bang, the PLC is going to read it and scan it and sync it all up and everything like that. And so there's a possibility that, you know, and this contact then would open it because it's a bit, and this contact would close because it's a bit, because it's been IO mapped. And so this might never turn off, which means this would never open, which means that when if this was a contact and it got written as closed, it would stay on. So if I push the jog and let up, the motor would just stay on because of the ladder scans. Okay, so you got to be careful. You can program this and get it and mess around with it if you want, and you can mess around with putting this IO into a map subroutine or not map subroutine and see what it does. But you just got to be careful. If you push that jog button and you let go, the motor might keep running. You're like, wait a minute, it was a jog. Yeah, but it was never turned off. All right. All the labs are going to use probably safety relays or safety IO. And so I got some examples here of a safety relay connection. Just get us back into the good stuff here. So here's is my safety relay. All right. So what I want to do is connections for safety relays used to start a motor, include dual contactor and monitored input. So what we have here is, you know, line 1, line 2. We're powering it up. The safety circuit, the dual safety, is going to be 11 and 12 here. So if I put in, you know, an e-stop right here, remember it's going to have a redundant set of contacts right there. That my redundant set of contacts would be here. This would go around here. It's going to come here like this. Okay, so these are redundant to there. Okay. And so I could just then wrap these around like this, and I would have a dual channel e-stop into there. But remember, if you have more than one e-stop, you could, you know, add another e-stop here with, you know, dual contacts, add another e-stop, you know, add it here, and then just wrap it around so that either one of those, pushing either one of those e-stops is going to break it. And when you're looking at this, you know, sometimes you'll see a dotted line around it like this, indicating that that's an e-stop device. Okay, and so on this e-stop, you could keep going, more e-stops, safety gates, more safety relays. You know, as long as they're redundant and coming back into these channels, then it's going to be good to go. Okay, now this wants used to start a motor. So what we want to do is we want to turn on a couple of motor contactors. Okay, so we're going to take, you know, these right here, and this is just line 1, right? Line 1, and we're going to come into our first contactor, K1, and our second contactor, K2. All right, and then those are just going to go to, you know, L2, depending on if they're AC or DC. So we're turning on a couple of contactors because on our motor, what we're doing is our 3-phase motor, we want redundancy, and that is going to be K1 and this is going to be K2. So both of those contactors need to come on in order for the motor to start. Okay, and then we're going to take a signal right here and we're going to do line 1, and this is going to go to the PLC input because we want to monitor the status of the PLC. Okay, so there we got that. And then the other thing it wants is some type of a reset. I don't know what it's called for reset, but that is going to be S31 and S32. So whether it's a manual reset like this, that you got to push the button right there in order to get, you know, that safety relay to reset or not, you know, that's what we got. That would do the reset. Now, the other thing would be the monitoring. It says a dual contactor monitored output. And so we need to know that these contactors are on when they're on and when they're off when they're off. So each one of these contactors is going to have auxiliaries on it, normally close auxiliary safety contactors. My monitoring is Y1, Y2. So I'm going to come here closed, and I'm going to come here closed, and I'm going to go K1, K2. Okay. So that is the way that this safety relay is monitoring this. So if for some reason, one of these goes down, boom, those pop open, safety relay breaks. In order for the safety relay to reset, both these contactors got to be off, then it will reset. If you break the safety, whether you break both channels or one channel of this, it's going off, you got to reset. And I'll go through and I'll show you that I'll hold, one of these contactors on or something, and then you won't be able to reset it because one of these monitoring will be off. And so this is kind of, if you remember, some of the basics of how we can use these different contacts here to turn these on. And some other things we do, maybe if we got it L1, maybe this goes to your PLC outputs. Maybe you want to source the output module through this, whereas these are doing the individual contactors. And that was the question, are you bringing down the entire output module? Or are you just trying to control one device? Or is this a master control relay that you want to bring everything down? There's a lot of different ways, to do this, okay? I'm going to pause for 1 second. Okay, let me just check. Let's be sure this is going like I want it to. Yep, okay. So let's come back to here. All right, so hopefully a little safety relay review, and you're feeling pretty good about that. All right, what we're talking about next is machine safety, and a lot of this stuff I just kind of stole from the internet right here at electricnewton.com. But you are going to see some machine safety out there, and a lot of what this course is designed around is automated systems, robotics, stuff like that. So we'll be doing a lot of that stuff. And basically, we're talking about what's been designed in to prevent hazard operations, moving parts, automated machinery, damage to the machine, damage to the person, right? We don't want to put the human at risk. And some of the big ones that we've seen downstairs at the Flex are your physical safeguards. That's kind of the number one. Just cover it up. That way nobody can get hurt. It can't always be the case, though. Your control system functions, such as emergency stop and interlocks, that's what we've been working on in this class. We did our e-stops, we did our safety gates, safety relays, safe operating procedures, and risk assessment and mitigation. We're going to talk a little bit about risk assessment and mitigation today. I'm by no means an expert, and you will not be after this, but you might have a little bit more appreciation or understanding of it, right? So once again, you're going to protect human life, number one. You're going to reduce downtime for injuries. Sometimes these are a little bit fighting against each other because the boss wants stuff running, but you want to be sure it's safe, okay? But it could lead to some costly penalties, legal action, shut down, employee morale. When employees know it's not safe, that's bad for morale. And you want your efficient production. And then once again, the other thing in here is just the damage to equipment when things aren't safe. That can lead to problems with production as well. So some of the things that we've seen on the Flex, or we've seen out in the workforce that we're addressing here, are mechanical hazards. Pinch points is a good one, or shearing points. A lot of this related to presses. A lot of it related to conveying systems, okay, rotating shafts, electric motors. So we're definitely have been exposed to a lot of mechanical hazards or talked about it. Electrical hazards, well, we're an electrical program, so we've talked about live terminals, arc flash, stuff like that. You got to keep in mind. Thermal hazards, we haven't done much with thermal hazards. We do get some people coming through here, like Meridian machine that deals with liquid magnesium, stuff like that. Could be a problem. Hydraulic and pneumatic. There's a ton of this out there. We've done just a little bit in here, but we haven't talked about the danger of it. Stuff that's under pressure is going to move. You got to be able to release that pressure. So that's a big one. And then motion hazards, unexpected machine start, conveyor start. Any system with stored energy or motion or high pressure requires safety measures. All right, that's a big thing. Stored energy or motion, you do need safety. And then related to this last one, this motion hazards. Just remember, bit memory status might not always be indicated on the machine as it's internal, okay? So if you have an internal system bit and you have an internal system light, Hopefully the light bulb's not burned out. That's saying I got system, there's internal bits going on in there, and there's the process is a go, but I just don't know it. You know, it's going to be indicated on the HMI or the lights or something like that. A little redundancy might not even be there. All this safety is controlled by tons of different standards. Here's some principles of the machine safety. These are ISO and IEC and OSHA, machine guarding and safety and complication in the US. There's just a ton. I threw the OSHA 1910 online, and it's right here. You know, here's some general requirements for all safeties: woodworking machinery requirements, mechanical power presses, mechanical transmission. You know, and this is just one, man. There's just tons of documents, but you know, it talks about this is for belts and pulleys and prime movers, and I'd like you to just kind of go through and glance through this a little bit, and you'll see a lot of it's a little bit redundant between the different categories. All right. But you can talk about, you know, once again, electric motor shafts, power transmission items, pulleys, your guarding, your belt rope. So, you know, like I said, there's different categories of gears and sprockets that you can kind of go through and get an idea, you know, of some of the general safety items. And it's going to be as it related to, you know, what we talked about, you know, here, you know, how it goes. So tons of standards going on. And so some of the types of machine safety devices that address this, once again, are physical guards. You don't want anybody to get hurt, you know, put a guard around it. You can't always do that. Emergency stop. And we've known e-stops. It might be an emergency stop with a safety relay. It might be just a 2-channel stop. It might require safety I/O or a certain processor like that. But you know, certainly we're continuing to study emergency stops. Light currents and area scanners. We do have some light currents that I think we might try and get into a little bit in here, just to talk about muting of light currents and stuff like that. Safety relays and safety PLCs. We're doing it. We're working with the safety PLC. We'll get a little bit into it in a couple weeks. Two-hand control systems. We already did the two-hand safety relay. We did the anti-tie down. Okay. Lockout tagout systems. You'll probably get training at work if you're working with any of this, so that you know you can lock yourself out and tag, and then get it tagged. Functional safety ensures that the system will perform correctly or safely in response to dangerous conditions. Key concepts. There's a safety performance level, okay? And that's ISO from PLL, A, B, C, D, and E. We're going to talk about this. Now, once again, I'm just going to introduce you to it. I'm not an expert. You could become an expert. It might be something the company really wants you to take a look at if you're in machine design. But we're just going to kind of do some basics on it here so that you understand what's going on. Another thing would be called the SIL, and that one is ISO, one's IEC standard, and these are kind of related. They're kind of for different types of machinery as well, and depending on where you're at around the country. So we're going to talk about performance level and safety integrity level. So redundancy and diagnostics, they need to detect and mitigate faults. So that's why we do a lot of monitoring of the safety relays, monitoring of the safety systems. And another thing today, a lot of modern machine builders would use safety rated PLCs. That's what we have. We have safety rated PLCs and systems, safety over Ethernet, safety I/O, everything like that to handle this reliably. And any equipment that you use for PLCs, for example, will have a safety rating on it. It'll tell you, you know, what the SIL rating of this equipment is. All right. Machine life cycle. So where are you going to be at in your life? I don't know. Are you going to design machines? You know, maybe you got to, if you're designing them, you're going to keep some of this in mind, and you're probably going to be a lot more of an expert than what we're going to go over today if you happen to be into design. If you're building them, which we have people in the panel building, some of the stuff's going to get spec'd out. You're going to be using safety components, safety contactors, safety relays, safety PLC, safety I/O, and all the proper installation of it. Same thing with commissioning. When you commission something, you actually need to verify and test and be sure that it all works like it should. And when you then operate it, you're going to have to be sure it works. You're going to have to get some certain amount of time on this system, be sure it is working. And then another big one, a lot of us are going to be in maintenance. And so when you're doing maintenance, you need to understand lockout, tagout, how to override the safety systems, how to do the diagnostics. And if something goes wrong with a safety system, heaven forbid, because it gets pretty complicated, hopefully you can understand how to kind of repair or maintain or update or change the safety, okay? So you do want to perform hazardous assessments on all equipment, new and legacy. So you got to test it once in a while to be sure it's doing what you want. Dual channel safety systems for redundancy. We talked a lot about dual channel. The safety gates and safety relays and everything from last time were, you just go crazy with it. What do you want to do? Install safety PLCs and networks for modern equipment. That's what we have, the safety PLC. That's what we're talking about, what this equipment's going to be rated for. You got to train your employees, and you got to have a safe culture, okay? So the first part of this is the safety performance level. In today's industrial environment, safety is about compliance. It's not just about compliance. You want to be safe for all the reasons we talked about, all the way from protecting human life to, worker morale. And there's different standards like this ISO right here, which introduce the concept of performance level, okay? So here's my safety performance levels. It's a measure of the reliability of the safety function that you're going to need for your system, okay? And how can you reduce risk? So obviously PLA is very low risk reduction, because you might not need very much safety depending on what you're talking about, and just basic alarms or hazards, very, very basic. And it talks about low risk, medium risk, high risk, up to your very high risk. And it gives you some typical examples here. If you have robotics going on, robotics are going to generally put you in this D category, C or D, depending. Conveyors, you're doing a conveyor. I think we're doing a conveyor in the lab, stuff like that. You're going to put you in C. And then this is like really, really dangerous stuff here, up to E, okay? Is going to be your different safety performance levels. So a safety circuit is a dedicated control pathway supposed to monitor, detect, respond to the events. Some of the things about a safety circuit that are different than like a stop circuit is the redundant. You have to have dual channels for your failure tolerance. You have to be monitoring them, and they have to be fail-safe. They're going to default to a safe state if you do have an error, right? And these are all things we've worked with: safety PLCs, relays, e-stops, sensors like light curtains, contactors with feedback. That means you got to monitor the status of the contactor, and obviously dual channel wiring, a lot of redundancy, okay? And let's say we're going to get more into it. So let's talk about determining the safety circuit for a PL. So you're going to need to do your risk assessment. You're going to identify your hazards. How often, or what's the frequency that you're exposed? Are you exposed to something dangerous once a year, or is it once a day, or once an hour, or is it just nonstop? You can die at any moment, right? You got to figure out your frequency, possibility avoidance, right? And you're going to determine your performance level. And your different categories are here. That if you're just talking about basic or single channel, or do you need some monitoring on it, right? This would just be like a magnetic dropout, or do you need to monitor the relay, or do you need redundant channels, or and fault detection and monitoring, or do you need just full all-out redundancy on everything, right? And that's kind of how you get your category in your PL level, okay? So you're going to select your safety rated components, and this MTTF, these values dictate the frequency. It's kind of time driven. How long is it going to last? How often are you going to have a safety issue? Things like that. And the manufacturing data will tell you the safety rating of the components. So we're not going to get totally into it, but that's what somebody's going to do. It might be you someday. You'll get more training, obviously, if you're going to do that. And so circuit integration wiring, are you doing your dual channel wiring for your inputs and outputs? your monitoring of your contactors and your cross-sort detection, and then verification and validation. Once you get it, you got to be sure you document, design it, and then it works like it's supposed to. I got stop categories here. So it says review the stop categories on page 3.3 of handout in categories of AB safety relay handout. So what I got going here is, okay, we did this. That's all right, I can kill this. I got this wonderful document right here. And what this document is the I think that it's, oh yeah, Phoenix Contact Safety Relays. And in here, it does talk just about a bunch of great stuff about, safety relays and what's going on, great table of contents. And then it shows all their different products. But the beginning of this document just talks about all the PL and SIL and everything that we're talking about right now, and according to the different standards right there, right? And so we're going to go over this a minute, like, what is meant by safe and how do you determine it, and your SIL and your frequency, and there's a bunch of math in here that you can do. Here's my categories. We just went to B, 1, 2, 3, 4. It really breaks down. This is something that I'm not going to go into because you can download this document and these first chapter 1, 2, and 3 get an idea of what we're talking about for determination of PL and SIL and kind of what's involved in it, okay? But what I did want to look at is chapter 3, which is some things. Take a look at this real quick. So these are just some safety technology basics, and this is our cross-circuit detection for category 3 and 4. The first fault must never lead to the loss of the safety function, okay? So when you start getting up there and you have a fault or a problem, you gotta, sometimes it's real easy. It's just, if you got a simple system, it's taken care of. But the more complex it gets, you have to continue to have, it has to be safe. So like your safety relay can't go down. It needs to still be powered, for example, all right? And this talks about cross-circuit detection, Maxwell cable lengths. There's some great stuff in here that you can take a look at about calculations for the cable lengths for these safety systems. But let's take a look at here. What I want to take a look at is the stop. And so there's different stop categories here. Here we're showing stop category 0. And this means stopping by immediately removal of power to the machine drives. Well, an uncontrolled stop. Well, hey man, if you kill the disconnect to the system, I guess killing the disconnect is a stop. It would be an uncontrolled stop. Now, hey, sounds good, but that's not exactly what we're looking for when we're talking about a stop or an e-stop or a stop category. And so you just got to talk about, is this just a electromagnetic dropout? That it's got memory and you can bring it down, and you're going to get an uncontrolled stop. You're just going to kind of cruise or wind down with its own internal energy, versus a controlled stop where you leave power available to the machine drives to achieve the stop. Power then is removed only when the stop is achieved, okay? Or stop category 2, a controlled stop with power available to the machine drives. You leave the drives booted up. And this kind of goes through and talks about, some of the different things. So I think you might want to take a look at 1, 2, and 3 here. Just kind of glance through them. It's really good stuff. And then also take a look at this document here is safety relays, and this is the Allen Bradley one. I've also got that out there for you, and it's here as well. And this is the stuff that we did last time. This just talks about what a safety relay is, force-guided contacts, redundant self-monitoring circuit. Remember, we went over this. You actually kind of programmed this just for fun. Talked about the different types. Here's the internal wiring of a safety relay, which you don't need to know. You don't need to know how some of this internal wiring is going to work anyways, because it just is going to work. Look for what opens and closes. But this is a great document right here. And once again, here's our emergency stop functions. We got ANSI and FPA versus the European. An emergency stop circuit shall operate, deactivate, or generate a loss of electrical supply. I'm guessing that's talking about like an electromagnetic dropout, like a start-stop, right? You're like, well, what about the disconnect? Not really an emergency stop, but that would drop it out. Versus the European market, there we're talking about what I just showed you: category 0, category 1, category 2, you know, all the way up to a controlled stop with power left available to the machine actuators. A lot of times that's what we're looking for, is a category 2 stop, but that gets more complicated. And then here's our e-stop. You know, reset shall not initiate a restart. Well, then you're going to need a safety relay or a safety PLC. So if you want to take a look at this document, it's super good to just kind of go through some of the basic stuff. And then, you know, later on, here's two-hand control. We already did this. This was from last year. I threw that in there. So take a look at these documents. You know, a lot of it talks about here, you know, what is the category zeros according to these different ones. NFP 79 is what we did in 131, is uncontrolled stop by immediate removing power to the machine actuators. Well, are you talking about the disconnect? Nah, not really. You're still talking about a magnetic dropout. Then these are your control stop categories, where you're bringing it to a stop and whether power is available or not. So you want to study these different levels. So we got a conveyor with an e-stop. Okay, let's just take a look at this right here. A conveyor line requires an emergency stop system that must halt motion immediately when an e-stop is pressed. Okay, so let's take a look at a conveyor system. And these are, we're going to take a look at this PL right here. So meaning of the individual parameters. So severity of injury. So slightly, a reversible injury. And I know this is hard to read, but you have this document. So a reversible injury, maybe get a cut, or maybe, I don't know, just push, you know, a bruise or something, versus a serious, normally irreversible injury might be like getting your finger cut off, or your arm caught, or something, you know, badly mangled. Well, a conveyor system or a stamping station could be, you know, something more dangerous. Okay, so this is the stamping station for a press. Let's just go back to this one real quick. This is a conveyor line, and so, you know, you probably can almost see this better than the other one. So let's think about that conveyor. So we're probably at serious injury, S2. That conveyor gets you or pins you. You're probably going to be S2 right here, right? The frequency, okay? So what is the frequency of this conveyor? That you're exposed to the hazard. Seldom, not very frequent, or exposed, or frequently or continuously exposed to it. Well, I don't know. It just depends on the conveyor. So a lot of conveyors, if parts are moving right there and you're working right with the conveyor, you're frequently exposed to it, right? Or maybe like a car wash. You're seldom, maybe you're not, if you're in the car, you're not exposed to the conveyor system. But if you're the guy coming in and they're, you know, brushing your car and the car's hooked up to the conveyor and they're waiting to let it go and all this kind of stuff, you know, that conveyor's kind of there. So maybe on this conveyor system, we're at F2, it's frequently. So we're start S2 and then we're F2. So we're headed down here. And the possibility of avoiding or limiting. Well, possible under specific conditions. Well, if you have good barriers and the workspace is designed, you probably can avoid the danger, but sometimes you can't. Sometimes stuff's moving fast, it's dangerous, it's open, exposed, you would get scarcely possible. But if you're looking like typically conveyor systems have guarding and or maybe a car wash, you know, you're on your side of the space. You know, those guys do walk across that stuff, even though I don't know if you're supposed to or not, and get trapped, but maybe you're possibly under specific conditions. So you went F2, F1, P1, you'd be looking at performance level D, okay? And so your components for a PLD is you need a dual channel e-stop button. You need a safety relay with cross circuit detection. You need redundant contactors to cut power to a motor. We just did that in the in class. And a feedback loop for the contactors to verify opening. So you need dual channel monitoring of the contactors, okay? And so if we go back to, you know, the one that we were looking here, once again, a stamping station uses a trim die for magnesium die. Well, that stamping station and that trim die is something you're doing all day. You're putting parts in, hitting the stop, it's coming down, it's cutting, putting the parts in, stop, cutting. And so what you're probably looking at is serious reversible injury. You're going to get your fingers cut off. Frequency is probably frequent or continuous exposure to that. So we're headed, down this way. And then what is the possibility of avoiding that? You're probably P1 right here, okay? But it could be P2 depending on, how fast things are moving, what the guards are, really the application. And so you're probably looking at a performance level of a D or an E right here, for this stamping station. And then you're going to have to pick your equipment and design your item to meet those. And we're going to get into it just a little bit more here, okay? So let's just talk about the safety intermediate functions, SIF. These are some acronyms. It's safety functions for the safety integrity level. The SIL is like the level of the PL. It's got a number on it, 1, 2, 3, and just like the PL's got 1, 2, or A, B, C, D, E. All right, and it's implemented by a system, a safety instrumented system to ensure the safety. It's designed to automatically bring the process to a safe state when they're met. SIFs, the safety instrumented function, are a critical component of the risk reduction strategy in settings. So what's the relationship? The PL versus SIL. So once again, PL is dictated by this ISO, SIL is by IEC, and this is kind of for machinery safety, PL, and this is broader. The SIL would be a little bit broader, but it still does apply, to machinery safety. But we're kind of looking at PL a lot. Risk metric, A to E, 1 to 3. Machines, robots, conveyors. We got a lot of that in Lansing. There's a lot of machines, robotics, conveyors kind of stuff. But we also have some processes, chemical processes, turbines, bigger things like this. And then these parameters down here relate to frequency, time, how it all works. So we got the in-class stamping station. So once again, we just kind of took a look at, our PL here, and how does that equate to, our SIL is in combination with the safety function within the framework of this. So we're going to say, the frequency of this in duration. So it's probably frequently, like you're stamping away, frequently, less than an hour. So I'm going to go right here with 5, okay? Probability of a hazardous event. So what is the probability of a hazardous event? I guess it's probably possible, that something bad can happen. You're going to have your safety systems, going on, right? But, it's possible. And then your avoidance of getting your hand cut off or something. Is it probably you can avoid it? Is it impossible to avoid? There's some things that are going on that you just cannot avoid it. That's probably not good, but it's probably possible to avoid it, okay? So if I add these up right here, I get 12. So if I get 12, I'm at my class 11 through 13 here, and I'm thinking that stamping station is going to be minimal SIL 2, and the event could be permanent, like loss of fingers, right? So it's going to have some severity here, and it seems to match up here with what we're looking at for this stamping station, okay? Because it's not going to be reversible. You lose your fingers, that's it. You're probably not going to be death, all right? If it was going to be death or loss of an arm, then with this number, it would be moved up to SIL 3, but we're probably just loss of fingers. So we're probably looking at SIL level 2 for this stamping station, all right? And so we kind of got a PD and or we got a SIL depending on how we look at it. So we're using the guard logic processors. So the standard ControlLogix processors can be used for safety applications, okay? But they require certain architecture and certified components and everything. And with the correct design and IO and everything like that, we can use the guard logic processors up to SIL level 2, which isn't bad, all right? But you're going to need safety contactors. You're going to need a lot of safety systems in there. With the guard logic processors, because the guard logic is redundant, there's a redundant CPU inside there. The old ones used to have a 2 CPUs that you took up 2 slots. The processor went on there, and then the partner went right next to it, took up 2 slots, the CPU and the partner CPU. And because you had 2 CPUs, you got double redundancy, and it worked. But the guard logic processor that we're using, the ELTE262, well, that doesn't need a partner because it's heavy duty. It's got the dual functionality built into it. And so these are kind of good for safety systems because they can get up to SIL3 or PLEE to build super safe systems up to SIL3 and E. Now, there's a lot of control engineers out there that are going to say, I don't believe that in a million years. Well, yeah, remember, there's still hardwired requirements for some of this stuff. The imaginary logic, the imaginary fiction is not doing it all. You still have a lot of hardwired components that are fail-safe. But the guard logics, because the redundant processor, can be set up to be fail-safe as well. So we're going to do lab 1, or lab 2, sorry, would be your conversion. You get, this is going to be lab 2, my bad. And what you're going to do is you're going to talk about, sometimes you get old things that need to be converted over, hardwired systems that were originally converted over to PLC. And today the systems are designed with PLC as the primary control, but we're going to talk about, what if you do get something and we convert it? We're going to convert a system over to just kind of get familiar with the Logix version 37, okay? Now, we're going to have some motors on here, and just want to reiterate that you want to use you want some monitoring of the motor, and some monitoring of the starter, some monitoring. You can do it through the safety relay, and you want to use the overload to bring down the entire system. If the overload trips, is a good idea to check the entire system and then require operator interface to get back online. Maybe, but you have a lot of different zones. Just because one motor trips doesn't mean the whole thing should come down. But in our car wash here, the main motors the entire car wash. So maybe we do want to bring everything down. So you got to think about, what about production efficiency? What about safety? What about functionality? What needs to come down? You bring in a system bit down, this program is going to have a lot of variations. Does the new system work like the old system? I guess that's the bottom line. Is it going to work like it should work with the old system? Are you making this more complicated? Are you making it less complicated? Are you just making it the same? I don't know, some combination of it. Does it actually work and do what you need it to do? That's the number one thing, right? But are you able to reduce components? You might be, PLC, right? Get rid of control relays, timers, counters, whatever. And what are the logic implications of stuff that's becoming bit logic? And is there training? Is there stuff going on that should be going on or shouldn't be going on? You got to keep these in mind. And can you incorporate additional safety? And is this safety needed? Is it easily incorporated? Is it a good idea? I mean, this is stuff that when they start retrofitting stuff, can some of the old safety systems just get put in the dumpster and the new stuff end up being a lot safer and a lot easier? Or do you reuse the stuff? So when we get these retrofit considerations, it's just good to talk about, what are you going to come up with? Logic 37, that's what you're using, looks a little bit different. And it's got a little more RS links functionality. I've got one pulled up here. And you're going to want to talk about, are you going to go with controller tags? I got a lot of controller tags here. Notice I've got my global IO here, my local, but I also almost, all my tags in this one are going to be, I used my global controller tags, whereas here, I don't really have any local tags. In my main routine, I've got a lot of I'm trying to be descriptive about what is going on here so that this thing works, like it should. Okay. Oh, good. Scale parameters. Oh yeah, we're going to get into this. Whew. So take a look and see what works for you, controller and local tags. It says quiz and lab. I will open the quiz up. Remember, you'll need safety classes. Talk about whether you use one or two safety relays. You probably do this with one safety relay and get the monitoring that you want of the contactors. You need to disconnect for a 3-phase motor. Be careful. And finally, do a good job with the lab paperwork. It helps me try and figure out what's going on with the name of your tags and in the descriptions of what the logic is and your I/O wiring diagrams and stuff like that. So a lot going on this week, and you're going to have to do some reading on the D2L, do some homework, do some labs. Should be a good one.